So in this chapter, we'll be talking about kinetics. So this may be a word you haven't heard before. Kinetics has to do with time. So this entire chapter has to do with chemical reactions and how much time it takes for them to happen. So the speed at which reactions take place is called the reaction rate. Some reactions can be fast, others can be slow. We can study these rates of reactions, and we can also control these rates in several different ways. So a reaction with a fast rate, here we have, our timer, and we have a reaction with a fast rate on this side, and then a reaction with a slow rate on this side. As we start off with our reactants, those are our major components in each of those at time 0. And then as you keep increasing time, as time goes on, we start to see that we have our product form for both of these. So for the left hand side, it's the little green circle, and then for the right hand, it's the pink. So a reaction with a fast rate, you end up with a bunch of product, let's say past 45 seconds. And then a reaction with a slow rate is taking longer, so you still see some of that reactant at the beginning and only a little bit of that product. Overall, this study of these types of reaction rates is called chemical kinetics, and we will look at step-by-step views of these changes from reactants to products, which are called mechanisms. So we're going to start off this chapter by talking about reaction rates. So what is a reaction rate? It is the concentration change over a certain amount of time. So any rate, no matter what type of rate you're looking at. So for example, speed, all it is a rate. So it's a rate of how much distance you're covering within a certain amount of time. And it's the same idea here, except we're talking about concentration. So for here, let's look at this example. We have C4H9 Cl being reacted with water, and it's making these products. And let's say we wanted to look at the average rate for it. We would take the concentration and divide it by the time. Now let's break this down a little bit. So rate is a change of concentration over a time period. So what we have here is first delta, which means change, like final minus initial. These brackets mean molar concentration. This T right here means time. So we have the change in concentration over the change in time. And overall, this gives us the rate. So we are going to first learn how to write rate expressions. So all these are those rates that we just talked about, how we have the change in concentration over a certain amount of time. Okay, so it's the mathematical representation of a rate of reaction. They will always be positive, and they can be written in terms of reactant or product. It doesn't matter which one. So first I want to zoom in here and take a look at this this table. So in this table, we have a lot of data. But let's just take a look at this right here. We have time points in hours, and then we have concentration. So mole times liters with the -1 for the exponent. All that means is mole over liter, which means molarity. So it's just a concentration. And what it's showing us is that at time point 0, we have this much amount of H2O2, of hydrogen peroxide. At 6 hours, we had this much left. At 12 hours, we had this much left. So you can see how it's decreasing, okay? Now, let's look at the actual, derivation, or just plugging in the numbers of it. So we have our final, or a second time point, minus our first time point in terms of concentration first. And then we have, T2, the actual time, minus T1. Now let's look at that filled in. So they actually took data of the table that we just talked about. So at T2, we had our time point was 6 hours, and we had 0.5 molar of our hydrogen peroxide. And then our initial was at time point 0, and we had 1 molar of our hydrogen peroxide. So at this point in time, our rate of decomposition, which is also up here, was 0.0833 mole per liter per hour. And if you look at a different set of time points, so in this case it would be 24 hours and 18 hours, the rate starts decreasing. So you can see how the rate is much, much smaller in comparison to at the very beginning. So as the reaction keeps occurring, the rate of decomposition will start to slow down because there's no more, there's no more reactant that you're starting off with because you have produced so much product. So we just discussed a particular reaction. We were discussing hydrogen peroxide and it decomposing into water and oxygen gas. Now, remember at the very end, I said and mentioned how the rate of decomposition changes over time. So at the very beginning, it's quick, it's fast, it decomposes, the rate is high. And as you keep, as the reaction keeps happening, it will eventually start to slow down. So you can see that here. So at the beginning, the reaction is pretty fast. It's decreasing in the amount of H2O2 over time pretty fast. And as you keep going, it, levels off. It levels off. So there are different reaction rate types. We have our average reaction rate, which is the rate within which a reaction proceeds over a certain time period. So this is just looking, comparing from the beginning to the end overall what the rate is. An instantaneous reaction rate is something that is kind of difficult to, calculate. So you can calculate using a graph of concentration over time. And then if you take a slope of a straight line tangent to the curve of that specific time, you can get the instantaneous reaction rate. So this is if you want to look at a very, very particular point in time, what the rate was. So again, this would take more work to calculate, but thankfully we don't. But you can do that. It does exist. And then finally, we have our initial reaction rate, which is the reaction rate at time 0. So you're looking at starting from time 0 to let's say 6 hours, how that first rate we discussed was looking at. So how are reaction rates affected by stoichiometry? Stoichiometry, you may not have heard this word since Chem 1. All that is the ratios of either reactants or products that are reacting with each other. So for example, in this particular equation, chemical equation, we have 1 mole of H2 reacting with, these are ones, even though they're not there, they're implied, 1 mole of I2, and overall they are reacting to produce 2 moles of HI. So that's what mole to mole ratios are, stoichiometry. Now, because of those ratios, the rate of change will be affected by that. So what we are going to do is, we discussed, a regular rate and how it's the concentration of your either reactant or product over time. We are going to add in a coefficient. Now we're going to do that by multiplying the coefficient by we're going to multiply the calculation of the rate, so the concentration over the time, times 1 over the coefficient. Okay, so for example, with hydrogen iodide, right here, to write our rate, we would take our 1 over and then the coefficient, in this case it's 2, and then the regular thing, which is delta, the concentration of HI, and then divided by the change in time. So all you do is take the coefficient, you place it, in a fraction 1 over, and that's how we add in our stoichiometry ratios. So in a reaction, you are going to have 2 things happening. The reactants are going to be used up, and the products are going to, start to accumulate. So when we look at rates of reaction relative to each other, we can see 2, different patterns. Reactants being used up, they will start off at a higher concentration. So for example, this NH3 right here. And as time goes on, then the amount of product, which started off at 0, will start to increase. So this is just something graphically that I would like you to understand. So now let's do a practice problem where we write a rate expression. So this one's pretty simple. All we're going to do is write the rate of decomposition of N2O5. So we're starting off with just the concentration. And then we're always going to divide by the difference in time. That's our basis. Now the only thing you need to add is the coefficient. And the way that we add the coefficient is that we add 1 over whatever the coefficient is. And because this is a reactant that is being consumed, we are going to put a negative sign. So here the rate is equal to this right here. In this problem, we're doing the same thing, except we're relating both reactants and products. So there's just a few things that we have to note. So let's call this A, B, C, and D. So for both A and B, we have a negative sign because this is being used up, versus for the products, we have plus signs, so positive. So that's about the only, major difference between these two, but for everything else, we're just going to write the rates normally. So we're going to follow this. This is a really good example. So the overall rate relating this entire equation, rates of consumption and rates of formation, would be, first, we have our 4 of NH3, and then, delta NH3 divided by our time equals, and then again our negative, and then we're looking at B now, so it would be 5. And for our first product, it would be 1 over 4. Then our product is NO. And you pretty much get the point, so I'm just going to write this. And that would be us relating all of the rates of consumptions to the rates of formation together. So just remember those negative signs versus the positive signs for the products. So finally, we have some factors that affect reaction rates. So chemical reactions, first and foremost, they occur as a result of collisions between reactant molecules. So this hasn't been, necessarily something that you may have thought about, but just think about it. In order for, let's say, me to get a job, yes, you can apply to a bunch of jobs, but networking is very useful. So the more people you meet, the more people you come in contact with, the more chance that you can get a job. So the same thing with molecules or compounds. The more they collide with each other, the more they collide in the correct orientation. And that's a whole nother section of this chapter. But for these purposes, just think the more collisions, then the more likely that your reaction is going to occur. So your reactants will start to get consumed. But as they start to get consumed, the collisions happen less frequency, and overall the reaction rate will decrease because you have product being formed. But overall, we do have 4 major things that affect overall reaction rates, which we're going to talk about. So first, we have the nature of reactants. So the more readily the reactants can collide, then the more rapidly they can react. So we have like a list of things in terms of what this means. Small molecules react faster than large molecules. They can move more. They can, collide with each other more because they're smaller, because they're moving more. So overall, this leads to a faster reaction. Gases react faster than liquids, and liquids react faster than solids. And again, remember how in the first chapter in this semester, we talked about solids, liquids, and gases, and how gases, the particles are moving very rapidly. And because of this, they actually, collide with each other more, so they end up having a faster reaction rate, and liquids are up next. The particles move around, and solids, they're not really moving. Powdered solids versus anything that's kind of like a thick block will react more. So, for example, here we have iron powder versus an iron nail. The iron powder reacts really fast with, in this case, HCl, versus the iron nail takes really, really long to completely react. And this is because for powders, you have more surface area. More surface area allows for more collisions again and causes a faster reaction rate. Certain chemicals are more reactive than others. This has to do with their properties of them, like intrinsic properties. Ions react faster than molecules. There's no bonds that need to be broken. They have their charge and they react in that way. Next, we have reactant concentration. So the more concentration of your reactant, or the higher the concentration of your reactant, the more likely they're going to collide with each other. So this is going to increase the reaction rate. Yeah, more molecules, more collisions occur. To show you an example, here we have steel wool reacting with 20% O2, and you can see it's burning. Any type of burning is just reacting with O2. Here we have steel wool in 100% O2, and you can see how it really lights up. So it's reacting a lot faster because you have more oxygen. I'm sorry about how plain this slide is. I usually try to have a picture in every slide, but I didn't on this one, so I'm sorry about that. Next we have temperature. So as you increase the temperature, then the rate will also increase. This is because of kinetic energy. Remember how gas molecules, they're floating around, moving around, and then the higher the Ke, the faster they are floating around, hitting the surface of the container, hitting each other, colliding with each other. So this is what kinetic energy has to do with that temperature. And then, temperature goes back and relates to reaction rate. So higher kinetic energy, let me just write this. Higher Ke means higher temp, and also means higher reaction rate. So at higher temperatures, molecules move more quickly, increases the collisions, and then this causes faster reaction. Finally, we have catalysts. So catalysts are components in a reaction that will not get consumed, so they don't overall affect the balanced reaction. They don't really partake in the reaction in that way, like being converted from a reactant to a product, but they do affect the rate. And they affect the rate by increasing it and making it faster. So they increase collisions, or they also can change the mechanism, so they'll make the pathway from a reactant to a product somehow faster, and that's all based on individual types of catalysts and reactions. But they also are involved in a lot of biological reactions, which I will give you some examples in that section.